Hello, everyone. Welcome to this episode. I say episode like it's a TV show or something, but it's not. To this video, essentially covering the different types and reasons why we choose audio amplifiers. So that is going to include tubes, Class AB, MOSFET, Class A, Class B, AB, Class D in different variations, different technologies behind all those. I'm going to use other people's videos and YouTube videos for these clips. Now, I don't know if that's going to get me in trouble. They may issue a copyright takedown strike. I don't know if anybody's going to actually see the video for that to be a concern. First order of business is, does the microphone work? Is the audio and video coming through okay? And then if we can get through that little bit, then I'll get this show started and we'll kind of go through the different tabs that I have. I'll try to narrate and skip through it as we need. If it makes sense, if certain things are a little bit vague, this might get very technical. And the reason why I want to do that and be technical is there's a lot of argument and preference around amplifier types or sounds or whatever that may be. And I'm trying to get to the bottom of it, not even just for my own understanding, but for argument's sake as well, to try and educate. We don't put a lot of emphasis on education anymore. It's more like there's more emphasis on being satisfied than there is understanding these days. So I want to do something of an understanding side of things. Oh, that's great. Now I've got somebody tapping on the pipes outside my apartment. There's been a crew outside my apartment for the last month or so. They've been restoring the brickwork around the apartment, which is really crazy to do in the close to winter. It would have been nicer to be done in the summertime. But now that it's like -10 outside, their use of the water is coming to a close. So anybody that's been on my channel before knows in the summertime, I had a flood in my apartment, and that's because they weren't turning the water off correctly. And in the wintertime, water pipes either freeze and sometimes burst, and that's what was happening. So now hopefully they're doing it the right way, and they're going to close that valve. So without further ado, what I'm going to do is just get into it. I'm going to start with valves, basically tubes, tube amplifiers, how they work, some explanation of it. And we're going to skip through some of these videos to try and get through the technology. And if there's anybody in chat, then give me a hint, ask some questions, let me know what's going on, and then we'll kind of roll through it from there. It is Thursday, December 4th, so we're going to just roll through this as best as we can. I'm learning for myself, but also I want to put this out there for anybody else who doesn't know how this stuff works. And if anybody's watching this after the fact, if something comes up that you don't agree with, put it in the comments. We'll just kind of hit these topics as we go. We'll see what's going on. Hey, Cracks is here. So I thought about you, and then I watched my notifications. Hey, you're online. Oh my God, look at that. The universe does work. We're here to talk about some amp stuff, amplifier technologies and types. We're going to try and roll through it, and I'm going to use other people's videos. You guys can see the channels here, so shout out to them. I'm going to try not to get myself copyright blocked after all of this stuff is going on. I want to understand exactly what's going on here, because in order to pick a very good amp or bad amp, or one sounds like this or one sounds like that, there's got to be a technical reason why. So this is the technical side of it. Let's just go and hear from Science of Loud first. I believe they're talking about guitar amps, but I think the technology is basically the same.
All valves operate on the principle of thermionic emission. A cathode is heated to a temperature hot enough that the electrons are provided the energy to escape their outermost energy levels, literally boiling them off of the cathode surface.
So essentially then what they're going to talk about is it goes through a control grid from one side to the other.
At the anode is a much larger version than what was applied to the control grid.
Right. So there's a signal here that is amplified through the control grid based on how much is allowed through.
Inside the AD30 we have 4 ECC83s, twin triode preamp valves. 4 EL84s, pentode power valves capable of delivering 15 watts in a push-pull pair. This amplifier has 2 pairs, giving a...
So they're talking a little bit more about the amplifier they're using rather than talking about how it works.
Without properly designed power and rectification, a valve amplifier is not going to be able to do very much. The AD30 is running a range of voltages internally, ranging from the small 6.3 volts AC to run the valve heaters and indicator lamp, all the way up to 335 volts DC for the anodes of the power valves. The mains plug supplies 230...
Okay, so let's see if we can get to... There's power amplifier section.
Forming the sound of the amplifier, the power amp section is there to make that signal loud. Leading into the power amp section, we have 2 pairs of EL84 pentode valves, each half being delivered an identical but phase inverted copy of the preamp signal to their control grid.
Okay, so there's our input signal. So say you have a source of some kind. In this case, it's a guitar amp. So the guitar is taking signal from their pickups down the line to their preamp, which I assume does something. They did talk about it here. There's a preamp section which has a whole bunch of other controls, types of things for a guitar amp. It's not quite the same. But this power amp configuration here is essentially the tubes are acting as transistors. They're taking in a signal and allowing a signal out, using the input signal as a gate control.
When one half of the valves conducts more, the other half of the valves conducts less. And when the signal voltage inverts, the valves swap their work.
So
this is what we call a push-pull arrangement, with each pair of valves working together to amplify the signal. One half taking the brunt on the positive hemicycle, and the other half handling the bulk on the negative hemicycle. This push and pull delivers a more powerful and more efficient amplifier than if the valves were operating in a single-ended arrangement, where all of the valves were amplifying all of the signal all of the time. The power valves in the AD30...
So this would be Class AB. Push-pull, from what I understand, is in this pair, they're using 2 tubes on either side to get more power out of it instead of just one set. So this is a push-pull, which means I think this is Class B. So this is the same concept for transistors in the schematic. Yes and no, not really. I'm going to move on to MOSFETs afterwards. I just wanted to start with tubes first. And in this case, it's a guitar amp, but it's still amplifying a signal, right? So I'm kind of picking through some videos here to try and explain a little bit, and I'm glad that I've got an audience that can ask questions, because the questions are going to help me guide through this. And now if I come up with something else, I can switch to a completely other video for explanation. And God knows I'm going to get something wrong, which is why I wanted someone that was an engineer or an amp designer to come on and actually talk about it instead of me using other people's materials. But I presented it to my friends group and my friends list, and nobody stepped forward, so I've got to do it this way. It would have been a great opportunity for someone to advertise, but, you know, not everybody's okay on camera. So let me just skip through this. There's cathode bias resistor and bypass capacitor. Let's see what...
are cathode biased, meaning that 1, swapping the valves in this amplifier is very easy and I don't have to worry about performing a rebias, and 2, it affords a little bit of natural compression from the power section, but that is kind of dependent on what class of amplifier we're dealing with here. The marketing detail for the AD30 claims it's operating in Class A, a very linear, if inefficient, amplification method. However, there is no physical difference in the topology between Class A and Class AB, a distinctly more efficient amplification method, even if some of those desirable even-order harmonics get cancelled in the process. It all depends on how the amplifier has been biased, whether it's operating in Class A, Class AB, or more realistically, a little bit of both, depending on how hard the amplifier is being driven.
Right. So at that point, I want to switch over to MOSFETs. And this one talks about the different kind of Let me see. Let me pull this off screen. That one, this next little section is going to talk about MOSFETs instead of valves. So that basically showed how a valve works. It's moving electrons from one point to another through the gate inside a vacuum tube. It needs to be like no air inside so those electrons can move freely. Otherwise, it wouldn't work. Yes, fairly the same, just need different setup transistors to do the same thing. Gotcha. Says that the class designations you need to understand according to what he said. Yeah, they're essentially talking about how they function and how they're wired. Class A, B, C. There's a class C. There's a class B type. There's a class D. Obviously, we'll get to all of those. So this one's about MOSFETs.
This is a MOSFET, and inside there's just a tiny piece of semiconductor. But these components are so important, and we find them everywhere.
Oops, hold on a second. I am sharing it, but it's not on screen. Derp. I'm watching it, but you guys weren't watching. Let me start over.
This is a MOSFET, and inside there's just a tiny piece of semiconductor. But these components are so important, and we find them everywhere. MOSFETs look something like this. They come in many shapes and sizes. They are represented with symbols like these in engineering drawings. I'll explain those later in the video. MOSFETs have 3 pin terminals, and we call them the gate, drain, and source.
Or I would say collector and emitter and base. I mean, I don't know why they're saying it's something different here, but yeah, there's different names for those. For audio, you generally catch class A, B, and D. Yes, we are. We're going to get to all of those. Never heard of class C. Yeah, class C is used in like radio antennas. It's very, very, very noisy, but super high powered. So like, from what I know, class C is used in like AM radio antennas, broadcast, and like very high powered stuff, but it transmits with a lot of noise on it, so it's no good for audio, but it's good for signal transmission. I won't be covering it because there's no point to really discuss it in audio terms. So yes, radio, I am correct. See, I'm not just a pretty face.
Times these terminals are in a different order, but we can check that on the manufacturer's datasheet, and you can find that online using the part number which is printed on the front of the component. I want you to imagine water flowing through a pipe. We can block the flow.
So basically,
there is a hole.
They're basically talking about now how a MOSFET transistor functions to allow current, or essentially amplifying this process. Now they're going to show exactly, like from input signal to output signal, what creates the louder part, like what is the amplifying part of it.
On one side of the disc, so if we slide the disc across, we can let water flow again. The disc is spring-loaded, and so it is normally closed. Another pipe connects to this disc, and the pipe is filled with water. If a small...
So in this example, what they're talking about essentially is this pin is what they're calling a semiconductor. That's the silicon in the MOSFET, which is what they're made out of. The silicon acts as a semiconductor, meaning when there's voltages applied, it functions at a different level. So I'm pretty sure that that's what this spring represents. This spring represents the resistance or the behavior of the silicon chip in response to an input signal.
Pressure is applied to this pipe. It won't be enough to move the heavy disc, but at a certain pressure, the disc will begin to move and allow the water to flow. As we increase the pressure, the disc fully slides across and the water can fully flow. But if we remove the pressure, the gate closes and the flow of water stops. This is basically how the MOSFET works. If we take a lamp and we connect it to a power supply, it will turn on. If we insert a switch, we can manually control this. If we insert a MOSFET between the drain and source pins, the lamp will remain off until we apply a voltage to the gate pin. And that means we can use a controller or sensor to turn the lamp on automatically. But
that controller is essentially, from what I'm understanding, is like the controller in that sense would be your source and or preamp sending signal or managed signal down to this phase. Now, I'm way ahead of myself there, but from my understanding, obviously you have a source, you have a voltage input or some kind of a change in level to trigger the MOSFETs in order to amplify further. So what they're doing is getting energy from a power supply through the lamp, in which case in our terms, that would be the speaker or resistor. And how much current goes through and how loud it is or how it functions is going to be controlled by the gate level.
We vary the voltage on the gate pin, we can vary the current flowing through the main circuit. And that means we can also dim the lamp as well as turning it on and off automatically. Instead of a lamp, we could control a relay, and the relay can control an AC circuit. And that means we can turn an appliance on and off automatically and even remotely. We could also control the speed of a DC motor.
So
the motor can rotate.
They're talking about a lot of control here. So let me see if I can get to some more explanation.
Will activate or deactivate the MOSFET. We can think of enhancement type like water in a pipe which is blocked by a disc. The water pressure on the gate forces the disc to move, and this will allow the water to flow. And we can think of depletion type like water being able to flow through a hole in the disc. But water pressure on the...
So I believe they're talking about two different kinds, PNP and NPN, which are these two
versions. If we look closely, we can see there is a small arrow indicating this. This arrow just refers to how the semiconductor is manipulated, but I'll explain that in just a moment. For the N channel, we apply a voltage across the drain and source terminals. For enhancement type, a positive gate voltage with respect to source decreases
this is very
the drain
nerdy
source
stuff at
channel
this point.
resistance, turning it on. For depletion type, a negative voltage with respect to source.
Okay, so I think that part of it is pretty clear how MOSFETs work. There's a couple of other things in here. They talk about how the current flows, how a MOSFET allows that current, and how the gate opens and closes based on pressure or signal. It doesn't really talk about it in terms of like audio. It just talks about how it turns on and off. So what we want to do is talk about how they're used in the signal. So let me move on to this other video by Headphone Show. So to control the flow of current, right? So current in our sense is like what allows the signal to like flow through the speaker itself, right? However, whatever state it's in, if it's positive, negative, or whatever the waveform is, they're going to show more in these videos. That input current or input signal is triggering what the MOSFET or FETs transistors, even if it's a tube, same thing, the gate control, it tells that gate how much to put in, right? So if you're pushing positive or negative, that's where, that's where some part of this that I don't understand. If I have one, then there's got to be a switch that says if it's a negative input signal, then it's got to be, something's got to pull the other way, push, pull, I guess, right? So you have pairs of these to push a speaker up or pull it backwards based on its signal, right? So the current is how much is going in. So that's controlled by, I guess, the preamp and source is going to say how much it is. There's how much reaches those things is like volume control. Enhancement type is akin to NPN. Obviously, depletion is akin to PNP. Yeah. So they're calling it different things, but essentially those are the same functions. And that's kind of what I want to get into here is how do they function in like amplifiers. I believe we covered how those technologies work, tubes and MOSFETs. Now we have, that's tube amps, which are class A as far as I know. I don't know that there's much class A, B in tubes, but maybe there is. Maybe that's, I believe that's just in the way that they're configured. I could be wrong. But let's just watch this video from Headphone Show. They explain it very well for these three types. Said you need complementary pairs unless you run Class A. So that's what I mean is I see complementary pairs, and then Class A is the current is always on, and it only changes with input signal. So there's no closing the gate. The gate's just always on. It just changes based on input signal. So if there's no input signal, it's still at full power. It's still running full current, but it's not changing, it's not. I need to actually find a Class A schematic or an example because, let's see if they explain it here.
Amplifiers used in audio are and how they work.
This is a little bit quieter, I think.
If you like educational content like this and want to support it, consider headphones.com for your next audio purchase. And buy with confidence thanks to headphones.com's 365-day return policy.
So thank you
there
to
are a
headphones.
number of different classes of amplifiers, but in audio we almost always see the same three: Class A, Class AB, and Class D. So we're going to focus mainly on those three. Throughout this video, we'll be keeping things simple and easy to understand, but if you'd like a more in-depth read into any of the topics covered, there are some great resources linked in the description. Let's start with the component that makes up the core of any solid-state amplifier, the transistor. This is an electrical component with 3 terminals that can be used to control the flow of large electrical currents using a smaller input current. Say you had a hose with high pressure water coming out when opened. You need a way of being able to control and adjust the flow of this water, since you can't just push back against it with your puny weak human hands. So
this is an excellent video, by the way. I mean, we're pretty much covering what we've talked about already. We've done the components and how they work. It's essentially a gate that opens and closes based on its input. Now we're going to try and see how they're configured in each type of amp.
Install a valve. This device allows water to pass
this is
through
the same
unrestricted
example.
when open, but when turned, needing only a small amount of force to do so, it can slow or completely stop the water. The transistor is the electrical equivalent of a valve, allowing you to control the amount of current flowing across.
And that's also why they call it a valve amp. I mean, they're all valves, so tubes are not exclusively to valves, unless you're dealing with Class D, and we'll get there later. I think all like MOSFET, GaNFET, vacuum tubes, they're all essentially valves. So, the elders may call a tube amp a valve amp, but they're all valves.
Terminals, the collector and the emitter, by varying the current to its third terminal, the base.
So here we see that we have these different names in this version.
Look at a classic BJT NPN transistor. Other transistors are available. Here we
hold on a second.
BJT NPN transistor. Other
transistors are available. Transistors are not safe for human consumption. Please contact your Oh my God. These guys are obviously just being funny at this point.
Transistors are available. Here we apply a constant DC voltage, VCC, to the collector, and current is allowed to flow from the collector to the emitter when the transistor is on.
So essentially from this, we're saying VCC is input. This is power available from the power supply. This is input coming in from the power supply. But when the base isn't on, there's nothing flowing. So there's no current moving through it. So depending on your input voltage across the base, it pulls or allows this pressure. I say pressure because of water, but it allows the power to flow through here to the load on this side. Now I'm wondering is if this is volume control allowing current, where does the signal part come in?
If there is nothing flowing into the base, then the transistor is off and it acts as an insulator and prevents current from flowing from the collector to the emitter. If you apply an input current to the base, this opens the valve and allows a larger current to flow from the collector to the emitter. The more you apply to the base, the more current flows across the transistor. And so by varying this current applied to the transistor base, feeding it a small version of our input signal, we can vary the much larger current flowing from the collector to the emitter, and in doing so get a larger amplified version of our input signal. But there is one more thing, and this is where the differences between Class A, Class AB, and Class B amplifiers come in. A transistor will actually only switch on once a certain input current to the base is achieved. It doesn't start at zero, meaning we need to make sure that the transistor base is always above that threshold or biased so that any changes to the input will automatically result in a change to the amplified output, rather than just falling below that threshold and doing nothing. This chart shows an example of the relationship between the input to the base versus the output from the emitter. You can see that there's a cutoff area where nothing is actually done, and then a linear portion where the current across the transistor increases proportional to the change in the base current. If we just left the input signal to the base as it was, then if we fed it a typical sine wave input signal like this, then the signal would fall below the cutoff area of the transistor and would not be correctly amplified. So we need to shift or bias the input to the base to ensure that the full signal can be amplified correctly. By connecting a speaker here, the small input signal to the base, which we've biased into the active region of the transistor, controls how much current is allowed to flow through the transistor and the connected speaker, thereby moving the speaker and producing sound. This simple setup is a Class A amplifier, one transistor biased sufficiently to allow it to drive the full input cycle of our signal. But wait, there's a problem. With a Class A design like this, we've biased our transistor so that even when there is no input signal, the static or quiescent current is still deep within the active region. The transistor is still on.
So here we get into efficiencies of the amps. So now I apologize to my audience. Nature calls, you got to answer that call, otherwise bad things happen. So at this point, I'm sure that they've explained the function of the transistors, how they kind of like pair to each other. Let me see. No, it shows how they function in an on-off state. Cool. So then in this section, they're talking about the terminology of biasing. So if it's a Class AB amp, or I mean, I guess a Class A amp doesn't have to be biased because it's always on. But in this case, maybe they're all sort of, Class A amps are always on anyway, so that they're always in their maximum position. It doesn't have to actually be pushed open or closed. I suppose in a changing signal, so your signal, it comes in and it's got positive, negative in order to make sound, then you've got that push-pull sort of configuration where the signal is moving back and forth. Then you need something to actually tell which power transistors to do the work. In which case, that signal would then push the transistor current one way or the other.
And current is still flowing even though we are not actually feeding any signal to the base, which generates a lot of heat and wastes a lot of energy. This is why Class A amplifiers run hot. They are always active, and any current not being used to drive the load of the speaker itself is just converted into heat. So how do we solve this? We make a Class B amplifier. A Class B amplifier uses at least two transistors, each of which handles a different portion of the signal. This top one is an NPN or negative-positive-negative BJT, same as what we saw in the previous Class A example. But the bottom one is a PNP or positive-negative-positive BJT, and the key difference here is that where the NPN transistor activates when you apply a positive signal to the base, the PNP transistor activates when you apply a negative signal to the base.
Cool. So let me see what's going on. Class A should be biased in near half VCC, just below that point. Okay, gotcha. Biased to half the input.
This means that when we feed our small input signal, the positive half activates and is amplified by the NPN transistor, and then when it becomes negative, the NPN transistor turns off, and instead, the PNP transistor activates and amplifies the negative half. Because of this shared duty and no longer needing to have your transistor amplify the full cycle of the signal, you don't need to bias it deep into the active region like we did with Class A. Each of these transistors can be biased right up to their activation threshold, allowing any positive or negative input signal to activate and be amplified by one of these transistors.
And there you get the efficiency of Class AB. So you're pairing a different type of transistor to do the other work, and they require less bias input current in order to have them active. So your input signal doesn't require so much power just to have them running.
But when no signal is present, neither transistor is active, making class B much more efficient. But wait, there's a problem. Transistors aren't perfect. They don't switch on instantaneously, and their activation region is not an exact turning point. Meaning, with a basic class B setup like this, there may be some slight inaccuracy
Here's
or delay
where we're going to get
when
into
one
distortion
transistor turns
levels.
off and hands over to the other. And this creates distortion in the
So something like that, obviously, you've got to know that's a switching delay. And this needs to be corrected in some of the circuitry. And I imagine this happens in many, many more places than just in the transistors. I mean, you're talking about how many different stages before it gets to your speakers, you know? And your speaker, depending on their sensitivity and a bunch of other factors, when it's being told and being pushed by the current, I don't know that they actually stop on a dime like that. If they're, you know, the suspension's moving and the current, whatever, is it going to stop here? No, it'll probably flutter a little bit, right? I don't know. But we're getting to class D, so let's just move through this.
The output signal called zero crossing distortion, which is why actual Class B amplifiers are very rarely used in audio. Instead, most audio amplifiers are Class AB amplifiers. These are still similar to Class B amplifiers, but rather than having the bias for each transistor set right to the activation point, each transistor is biased a little bit further, meaning that the top transistor will amplify the full positive cycle of the signal and a little bit of the negative, whilst the bottom one amplifies the full negative cycle of the signal and a little bit of the positive. Both transistors are active around the zero crossing point, eliminating the zero crossing distortion that would otherwise be present when you suddenly switched from one transistor to the other, whilst still being much more efficient than a full Class A amplifier, due to not having such an extremely high bias and constantly passing high current even when no input signal is actually present. So, Class A amplifiers can be designed more simply and are often sought after due to the arguably cleaner approach to amplification.
So now they're
with
going to
no
do Class
amplify
B.
the input wave. Work in a completely different way to Class
Class
A,
D.
AB, and B amplifiers. They do not directly amplify the input waveform itself by continuously varying the current passing through a transistor. Instead, they create a series of high-frequency, full-amplitude pulses, and their output can only ever be on or off.
This is where, this diagram right here is where I start to lose my mind a little bit, because I needed to look into this, what they're calling a comparator. So this is the triangle wave or saw wave that's coming in here is a clock signal. So this is a clock signal of on-off, essentially. And the comparator uses an input signal in order to generate a pulse width modulation signal. I believe they're going to explain it here. But I need to figure out what's going on in this comparator, because it sounds like that's where some of the quality output is going to be coming from. This is the part of Class D I really need to figure it out. So let's pause here. So for me to really understand something like that, I would have to build it, but I get the concept really well explained. Yeah, these videos, these guys here, and I hope I'm walking through the different types of technologies, like what a transistor is and then how it's used. Like, it's one thing to say, yeah, here's a transistor, but without explaining how it works, then you know what I mean? Like there's guys that look at amplifiers and say, okay, what transistor does it have? Is it made by this person, this person, this person, this company? Were they matched? Like matched sets of transistors in a build, like I believe the Agostino Class A amps, they're all matched pairs, like bias matched, level matched pairs of transistors. So the entire amplifier is balanced component for component. That's no joke. You're talking about a very, very labor intensive testing and building and pairing and then building an amp with all components that actually measure and function at a base level all the same. Like, that's intense. There's no wonder why that stuff costs like $80,000, $100,000. But this is why I wanted to get into the tech, is to comparator should be called a modulator. Well, I think they're calling it a comparator because in a digital sense, because this is an on-off signal, but receiving signal from a clock. And I'm going to make a comparison to Class D and computers in a second, because we all know computer chips are made of transistors. But why we not use computers, computer chips and transistors in audio? because, well, one, because the voltage level is much, much higher. And I think that there's a switching on and off thing that doesn't need to happen for audio, but that's where GANFET's going to come in. We're going to get there. I have links and tabs open here. There's still like 12 tabs to go through, so I'm going to try to get through this faster. So do I need something like that to get something better to my Kinky Studio, for example? I don't hear any difference more when it gets more expensive than 3. So here's the interesting thing. Like, I want to get to that and towards the end of the video here. And I need to get, there's still 12 tabs. I could be here for another hour. Because I want to understand that exact question too, is what differences, what is the diminishing return to spending more on some of these components when they're essentially all the same components, right? They're all using transistors. They may all be using linear power supplies. Well, now what makes them more expensive? Is it the components themselves? And in some cases, yes. Some capacitors, some resistors, some inductors, crossover components, some cabling, it all makes a difference to a small degree. But when you add them all together at an exorbitant amount of pricing, then it does make a sound difference. You can actually hear those differences, but you're not going to be able to hear those differences with like $200 speakers. So it all has to get better and better and better. There's no argument about does it improve, because yes, it does, but is it worth it is a completely different question. It's just a PWM, modulator, frequency modulation. So that's what I'm wondering is here, the switching output stage. So is this the modulator or is this the modulator? Because I think this is comparing and creating the pulse modulation, and then this switches it. So it's really the engineering design that starts it all, but I digress. Well, I mean, yeah, the engineering. I mean, I'm saying the components and everything function the same. It's just how they're put together. You know, they all kind of do the same thing, but what else is going on? Like this isn't talking about feedback loops, right? There's lots of other stuff that's implemented there. So I don't want to confuse the topics. Like we could sit here and just jump all over the topic and never look at my tabs. If you guys want to just carry the conversation in the chat. It says, for example, Canton, I didn't hear a difference. So on those speakers, you didn't hear a difference between, what did you say it was? What I don't know the price difference. First of all, I don't want to mix price with design. Right? Like I know a lot of people like to ask that question. You'd be like, yeah, but how much is it? I'm like, that doesn't, throwing money at something doesn't make it better. How it's designed makes it better, but some designs cost more money. So it's like, that's a different question. So yeah, it is interesting. That's why I want to get through this. The switching output stage is where the power is applied. Compared is where the signal is mixed. Yeah. See, True Voice of Reason is an engineer. He knows what he's talking about. So he's jumping all over this topic before I've even gotten to it on screen. That's where I'm getting confused. It just doesn't, I want to actually get through the videos here so we can actually see it explained rather than just reading it. So be patient, Padawan. Actually, I'm learning from you in this case. All right, let's see what they say about Class D here, and then I'll skip through the next few.
Let's examine the setup for a typical half-bridge Class D amplifier. This has a triangle wave generator and the analog input
so
signal.
We see that that number there, right? 5,000 kilohertz. That's how fast the pulses are. That's the frequency at which the pulses are being generated. The new versions of Class D are double that. More than double that. There's some that are 1200 kilohertz or 1 megahertz now. They're switching much, much, much faster. So that might come into. Sorry, dude, I'll slow down. Yeah, I don't mind. I don't mind getting into detail on what's on screen, but if we jump ahead, then it's going to be very confusing for a lot of people who don't know, right? Like that's the interesting part.
Which are fed into a comparator. This comparator is a circuit or component that looks at which of the two inputs is higher than the other. And this comparator feeds a switching output stage, which is a transistor that can switch between fully on or fully off extremely fast, hundreds of thousands of times per second at least. If we overlay the triangle wave signal and our sine wave input
So
signal
this is
being
where
fed to the
Class D
comparator, we can get a better
is
view
interesting.
of what's happening. At any point where the input signal is higher than the signal from the triangle wave generator, the comparator sees this and tells the switching output stage to switch on. And at any point where the input signal is lower than the triangle wave, the comparator tells the switching output stage to switch off. This leaves us with a series of high-frequency, full-amplitude pulses of varying width, according to whether the signal was higher or lower than the triangle wave at that time. This is called pulse width modulation, and to get the intended amplified analog signal from this, the output of the Class D amplifier is passed through a low-pass filter, which filters out the high-frequency components from the signal. Think of this as restricting how fast the output is able to move up or down.
Right. So here in early Class D, I'm going to say that the switching that they were talking about is because it was switching at 500,000, which is a lower frequency, at or above the threshold of hearing, you get high frequency artifacting if their cutoff isn't good enough. Like if the filtering isn't good enough, this is the part where a lot of early adoptions or early examples of Class D was not that great because they're switching frequency, and then their filtering process wasn't able to take that edge off. You could still hear it. I imagine really, really bad DACs do the same thing because a DAC is digital to analog. And in order to get that right, clocks are important. Otherwise, it creates that same sort of like crossover distortion or jitter or whatever that is. The timing is off, and our brains are sensitive to timing. So this noise is the same kind of thing. It's like leftover chirps and clicks and artifacting that creates harmonics that our brain can pick up on.
As a simple visual example of this effect, this is a 1 kHz square wave, but it's only a square wave because it has lots of very high frequency components. If we start to progressively filter out these high frequency components, we see this 1 kHz square wave transform into a 1 kHz sine wave.
You see how it cleans it up with the filtering. That's a very, very good animation.
Components. If we start to progressively filter out these high frequency components, we see this 1 kHz square wave transform into a 1 kHz sine.
And that image there that was on the side shows the distortion levels and how low the audible distortions are versus the primary signal.
Sine wave. A Class D amplifier filter will try to remove anything above 20 kHz so that all we are left with is the waveform consisting of audible band content and no unwanted ultrasonic components. If you've seen the DAX 101 video, you'll be familiar with the Flappy Bird analogy.
So this is
DAX
interesting.
And Class A or AB amps control the output by telling it exactly what to do, exactly what amplitude it should be at a given point in time. Whereas 1-bit Delta Sigma DAX and Class D amps use a method best explained by Flappy Bird. You want to follow this path through the pipes, but you can't just draw a line with your finger and have the bird follow it.
It's an interesting comparison.
Pressing and holding your finger to provide a 100% go up instruction, or letting go to provide a 100% go down instruction. The more frequently or the longer that you press, the faster the bird moves up, and the longer or more frequently you let go, the faster the bird moves down. The exact same thing is happening with the pulses produced by a Class D amplifier.
So if we were to draw a line of that bird flying there, it wouldn't be choppy. It would be fluent. It would have like a waveform. It would move like up and down over time. You know what I mean? So that's where like this idea of Class D being digital, sure, it's digital in the terms of like being on and off, but this bird is like a speaker cone to me. It still has some fluid motion. Certainly if these pulses are faster, it'll move closer to the input signal, then
and the low pass filter effect
you'd
of
be
Flappy
able
Bird
to see it.
is simply the fact that the bird does not instantaneously hit the top when you tap the screen. There's a restriction on how fast, meaning how high a frequency, the bird can change direction. So, Class D amps and Delta Sigma DACs are playing Flappy Bird, and R2R DACs and Class A amps are playing Forza.
And I don't understand that comparison. You'll probably have to watch that other video. So I want to move on to another component. This is going to be, I'm going to have to skip through this. This is a very popular guy. He's talking about op amps here. And I want to just skip through the intro to try and talk about how he's going to talk about analog math and how an op amp is actually ahead of the signal coming in. And then we'll talk about some other stuff afterwards.
At its simplest form, a voltage amplifier. It takes two inputs and amplifies their difference by a gain so high we typically assume the gain is infinity in an ideal case. In reality,
We'll skip the humor.
infinite gain and you can draw as much current as you want from its output. In reality, none of these are true, but we can work with these assumptions. You know what they say, fake it till you make it, and that's when the reality hits you. That's all. A simple thing with the
let's see
rails,
how they
as we
work.
call them, that power the circuit. Op amps are one such circuit. Ideally, I said ideally. So in an op amp where we now add two other terminals to show the supply rails they
So VCC is the same as the transistor input, and then VEE ground is like the opposite.
ride on, the output voltage will jump to the power rails and no further. So you could say the gain is ideally infinite as long as the output voltage is within the power rails. So with the
So that positive and negative of an op amp, that's your input signal. And then the output, this is controlling something. I don't quite understand yet, but I believe he's going to go into it.
ideally infinite as long as the output voltage is and our output is high or low, like a digital circuit based on which input is higher. If we aim to compare only, there are comparators with the same symbol that perform
Comparator. See, comparators is the reason why I want to show this video. Op amps are functioning like a comparator, I guess. I'm not entirely sure.
better than op amps to create a digital output. Op amps are designed to perform better in an analog circuit, although you can use them as a comparator as we see here. I'll talk about comparators in another video. So as you can see, the output jumps to the supply voltages. As you can see, the output jumps close to the supply rails in typical op amps with some voltage difference. Only in rail-to-rail op amps can the input and output voltages get real close to the supply rails.
So they can operate as comparators. Right. So they are used in analog, sort of like they're used in analog signals, which is essentially like used in amplifiers for the input stage before it sends the output to the transistor or the amplifier section. This is a component that fits in before the amp types.
What makes op amps really spicy is when you add feedback to them, where you somehow connect the output
so
of the
this
op
is
amp.
like what I was talking about with feedback in the signal. So how these work to correct their output to make sure that it stays the same on the output side. So let me see. I don't want to watch the whole thing because like he's got 8 million subscribers, so I don't really want to copy everything. Let's jump through it, see if I can get to something else.
You use it along with a stronger negative feedback, its output is digital and falls under comparator applications. Subscribe and stay tuned for the next Electroboom 101 on that. What we really like for an op amp though is a negative feedback. If V- is slightly higher than V+, creating a negative input delta, it pulls the output back down, bringing V- close to V+. Similarly, if V- is lower than V+, creating a positive input delta, the output goes positive, pulling V- close to V+. Stability. So the output has to stay still between the power rails with a known value. This means, assuming an infinite gain, the delta between the positive and negative inputs must be zero. So we can assume both.
Right. So that is like a control in front of That's a control in front of the amps. Now, I'm going to use a little bit from Paul's thing here because somebody asked him, why do tubes sound different from transistors? So I'm going to say that's an intro. There's the question. Here's his answer.
We've been in business up until just recently. We never had tubes, though I loved their sound in any of our equipment. And the reason was simple, for what you state. Tubes, while they have a great sound to them, and they are now in our BHK products,
Yep.
the preamplifier and the mono and stereo amplifiers, sounding terrific. They do have to be replaced. Tubes don't last forever, and solid state devices essentially do. So that was one of the.
So let me see. What's the area of linearity? Let me see. I don't want to use the whole video because that's where I'm going to get copyright flagged and
On very high voltage,
a lot of shit.
where a transistor might run on 15 volts, maybe 20, a tube runs on 100, sometimes 200 volts. So there's a very big difference. And one of the first things
So
we
the
see
efficiency of both
from
is
high
different.
voltage devices to low voltage devices is the area of linearity. Every device, whether it's a tube or a solid state device, has an area of linearity. And if you were to see the curve of linearity, what you'd want to see is from the lowest to the highest, you'd want to see a straight line, so that for every level of amplification within its range of its highest to lowest voltage, it is linear. Voltage in equals voltage out.
Right.
But in a tube or a solid state device, you don't see that. At the low ends, you have this kind of a curve. Then in the middle, you have sort of this straight line linear region, and then at the end, it S's out too. So it kind of
So it's most linear in the middle of its voltage range.
is linear. If you are running that device at 100 volts, you've got 30 volts of linearity, just to keep it simple. Don't get all wiggy on me and start quoting formulas and crap. I'm just trying to explain things simply, okay?
Trying to get
Some
to
of
his
you
explanation
just
for
get
the
all
sound of
around.
either one.
Start shaking.
Paul's amazing.
Has a greater linear area than does a lower voltage device, typically a solid state device. Tubes also draw almost no current on their input, where a transistor like a BJT is a current amplifying device, and a tube is strictly a voltage amplifying device
Okay.
when we're concerning its input. A FET, or a field effect transistor, is the closest thing you're going to get to a tube, and it too, although it does draw a little, it's kind of a hybrid, it draws a little bit of current, but mostly it's a voltage amplifying device as well, like a tube. So they're closer to tubes. The sound
MOSFET.
of these devices is definitely different. And anybody who will tell you that three devices, a tube, a BJT, and an FET, running at the same voltages, relatively, in terms of signal level, at the same gains within a specified area that is not outside their range, does not sound different because they don't measure different, is full of you-know-what. I'm sorry.
So they do
just
sound different, but
do.
why?
And there are a number of reasons for it. And these videos are too short to go into all of them. Quickly, a tube power amplifier, if it uses tubes on the output stage, that's a whole nother ball game, because there we have basically a high impedance device that is trying to drive a low impedance speaker. Typically, we have to match that with a transformer to make up the difference in impedance. There are things called output transformerless, or OTL amplifiers, and those amplifiers have rows of tubes that are driving the speaker directly, but those are rare. So if we're going to use tubes, in our opinion, we want to put those tubes in the input stage where they do the most good. And in our designs of amplifiers, we use vacuum tubes on the input. In our solid state amplifiers like the Stellar series, we use field effect transistors, or FETs, on the input, which very much sound like tubes, and that's how we get a tube-like sound. But transistors will never sound like tubes, and tubes will never.
So he doesn't really explain why. Thanks a lot, Paul. We got through that whole video with Paul, and the guy, he says, yes, there's a difference. They can never sound the same because of lots of things, and we don't have time. So thanks for not answering the question. Sorry, everybody, for... I thought maybe, you know, a guy like that would actually have an answer there. No offense to Paul, but damn it. I need to skip through some of this. Push-pull pairs and Class A, B, B, A, B, A operation. So this is basically some electronic diagrams here to talk about how they function. I think he's doing all of the math here for the output. So let me just get to this point.
0.4 volts. So now the output is following the input precisely. In the output now, you have an exact copy of the input signal.
So right here is also showing the 0.7 volt offset to make sure that they're crossing at the same point. And this is push-pull Class A, I believe. So this is one side and the other side. And I believe he's going to move into Class AB here.
We have a small current here that make the two transistors conduct when the signal is zero. This is very important because now let's imagine that we have the positive cycle working. We are on the positive cycle of the signal. When we are on the positive cycle of the signal, the NPN transistor is sourcing the current to the load. The NPN transistor is making the work, is working hard to follow the input voltage on the output.
So
the PNP transistor will start to conduct. But the NPN transistor will stay conducting for a little bit, even on the negative cycle. Because even if we have...
he's explaining electrically here some of the numbers. He draws this map of them overlapping, push-pull. Hopefully this is entertaining. Here, let me see. I want to show, we've shown a lot of stuff on how the transistors work. So let me skip this. This is a different video here. This is by Kiss Analog. He's talking about how Class D functions. Now this will be an explanation how the pulse width modulation recreates a waveform. Now we've seen that the input signal of analog and op amps and how they function and to control and how to move that sound and why they may sound smoother, they might sound warmer, they don't have to deal with the same noise problems. I mean, this whole video is to talk about the technologies and devices for either type, why someone wants tubes, why someone wants solid state, why Class AB is revered the way that it is and it's the most popular. Is it the best between the two worlds? Is Class D still missing something? I know what I've heard. Obviously, I'm subjective. But maybe there are reasons in the technicalities and certain components why they sound different and why people don't like them. So let's just get an explanation here on Class D, and I'll try to move through the rest of this as fast as possible.
All right, I've got my board. And sorry about the drawing in advance, but let me go over the circuit real fast. The output of a Class D amplifier might look a lot like the output of a Class AB amp. Push-pull circuitry. I'm using switches for my transistors. So you might have a switch up here that's pulling the voltage towards plus, and then that turns off, and this one turns on and pulls it towards minus. So one pulls it up here and one pulls it down here. And yes, it's a square wave. That's the difference between a Class D and a Class AB.
So in this drawing, he's got drive control written here, which I'm assuming is going to be the comparator and switch operator. Doesn't really seem, maybe it is because that pushes the current or the power supply up, on and off.
AB, these would be, the transistors would be working as amplifiers. They'd be amplifying the signal that they see. Where in this case, we don't want to dissipate power across these transistors. So we just turn them on, turn them off, turn them on, turn them off. And if you do that and you modulate the pulse width, then you can, the overall RMS voltage out here, you can change to be what you want. And for instance, if you start off 50% duty cycle, you're at the plus voltage, the same amount of time you're at the minus voltage. So the voltage, your RMS voltage out here is going to be 0. But then when you start going, you know, this guy starts
Doesn't
to stay
explain
on.
the pulse modulation here. So this is input and output power. Don't need to see the setup. Power supply, scope, probe, zooming in. So I want to see him explain the wave formation. This is a little bit more nerdy than I imagined on this side. Let's see. Let's see him showcase the wave.
I'm going to zoom the main time band.
It's
just
very,
so we have
very
a
good
cycle or
channel. If
two
you guys
look
want to
at,
know like a
just
lot
to make
more technical stuff, then I
everything
do
else simpler.
recommend his
Okay, we got a
channel.
couple cycles
There's a
there,
lot
right?
of really
Now I'm
technical
gonna hit the
stuff
zoom
going
button.
on with how this stuff works.
And we're going to zoom right in on that. And let me see. I'm just curious. I didn't even check. Okay, my record length is set for max. That's good. Deep memory. Awesome. Get good resolution even after you grab that much information.
So this is zooming in
right,
on the signal here, and you can see how tightly packed these pulses are in order to make this wave. You could barely see any kind of like movement there or anything on the scope.
Guys, you know what? I think a few people bought this scope since watching me do this. It's time for GW to help me out, right? All right. Well, maybe someday. Okay. Now, what I'm doing is, see these green brackets up here? And this is our...
So he's going to zoom in.
That's our 0 point. We're zooming in right there. Okay. Look at that duty cycle. Doesn't that look like about 50%? Let's get the cursors. Now, when I hit the cursors, you notice, you see the cursors right here? So
I'm trying to look for, to explain what we're looking at, I'm trying to look for the frequency input. It's 24 volts RMS. Duty cycle. I don't see... Yeah, I don't see a frequency for the pulses. I see a voltage, but I don't see the frequency zooming in on.
slide
But
it
essentially,
over here
that's what's going on is...
where it's in that green window, and then I can see it starting to appear. Okay, and I got them both locked together. That's pretty awesome. I didn't mean to do that. That was just dumb luck.
Yeah, so
Okay, I'm
there's
gonna
no what they're
switch over to
calling...
The
Like
first
that
one.
on-off signal is very, very fast for the pulses. No, I don't know how much of an explanation that is. Let me see how what else we can get to. This one's a whole other type of video talking about the differences between GaN-FET and MOSFET. So silicon versus gallium nitride. And I mean, gallium can be switched faster, but I don't believe they're being used the same way. MOSFETs are usually class A Bs, and then GaN-FET is being used in class D amplification. So
What's up?
why?
Eddie Alho here with KissAnalog.com. All right, so
Let's get the board out.
I tell them what I'm going to use them for, and they decide if that's valuable for them, and so they do. But obviously, there's no hooks or anything like that. They just send them to me, and once personal data. That's how I got that one free. But all right, so what I want to do is I want to just talk about the GaN-FET, the gallium nitride FET, and there's a figure of merit that they have with MOSFETs or FETs, general. And so the GaN figure of merit just looks a lot better than a MOSFET. The two main characteristics they use for
I
the
hope he
FOM
draws it.
is the RDS on, because when a FET turns on, you want it to be ideally 0 ohms, but there's some internal resistance, so that's the R drain the source on resistance, RDS
Okay.
on.
So there's inherent function inside of the material that is better in a GaN FET than a MOSFET. MOS stands for, what is it? Something silicone? Silicon? Monooxide something. I don't know. I don't know for sure, but I'm pretty sure that's what it stands for. Something silicon.
And it's in milliohms for the kind of FETs that we normally use.
So before he even explains it, I have a feeling that factor, those reasons there, those properties limit its switching ability, because there's a certain amount of resistance or impedance in the material that it can't be switched faster because it doesn't dissipate its own properties.
Our voltage ranges. And then there's also, you have to turn them on, and so you have to put a voltage on the gate. They're voltage driven devices, not like a bipolar junction transistor that's current driven. You have to put current, and then the gain is going to take that current, multiply it, and give you a collector to emitter current gain. But in a MOSFET, you put a voltage on the gate, and as you increase the voltage, the thing turns on. Okay? And so as you turn it on fast, like in a switching power supply or Class D audio amplifier, you're going to have to charge and discharge that gate, and that's they call that the gate charge. Okay?
So the gate charge is
there's
too high.
Internally, basically, some capacitance from gate to source.
Okay.
And this is the threshold.
So that's essentially what he's explaining there between the MOSFETs and the MOSFET and GaN FETs. The GaN technology is a different material that can be turned on and managed and switched faster with lower power than MOSFETs. And it's expensive to use now because it's being introduced. Now, what is the sound difference in those? Let me see. I have a bunch of other videos here, but this video is already an hour long. Let me see. So let's just watch this short, and we'll see if this one explains it.
Ever wonder why your speaker sounds amazing or terrible? The secret might be in the amplifier. There are 4 main types of audio amplifiers, and here's how they work. Class A, always on. The transistor conducts 100% of the time for the cleanest output. Class B, 2 transistors take turns. One handles positive, the other negative half.
But it has the crossover distortion.
Class AB, like B, but both transistors slightly overlap to reduce distortion. Class D, rapid switching on and off creates pulses, then a filter rebuilds the sound. Know your amp, know your sound.
So
don't just
that diagram. This is what I want to look at. You're obviously seeing there's diodes there, there's transistors in this signal as well for power, and this looks like the comparator. So in all of these different examples here, I haven't seen a good explanation for how they actually function. So let me see if I can draw up a diagram or something on how they work. So it's a GaN converter. No, we don't want that one. Let me see. Let's watch a little bit of this guy's video.
Why would it be any better than a linear amplifier? Well, amplifiers, in a similar fashion to power supplies, come in linear versions.
I love the characters that are making these videos. It's fantastic how
are more inefficient in general, but are also
we get
less
so
noisy.
many different kinds
The main
of people
reason
that
behind this being the way in which the
fascinated
amplification
in
or
this.
regulation element is used. So, with the linear amplifier or linear power supply, the transistor is used as a variable resistor. Based on the signal that needs to be processed, an equivalent resistance
variable
is generated.
resistor based on, so like we're talking about the transistor being open and closed. It functions to allow some current and not a lot of current. Yes. Class AB.
Into a sine wave. Well, the different classes of switching amplifiers achieve this in different ways.
Class D.
And the Class D amplifier that we are talking about today relies on the principle of generating a square wave and then filtering it using a low-pass filter to recover a modulating signal. So, if you take a square wave signal and you filter it using a low-pass filter, you will be able to get a DC output whose amplitude is equal to the on time divided by the period times the amplitude of the initial square wave. So, for example, if you low-pass filter a 50% duty cycle square wave, you will be getting a DC level equal to half the amplitude of the initial square wave. Now, that doesn't sound very useful.
Right. So explain how
How
that
do you
works.
then filter out the square waves?
The
to recover
interesting thing
useful
that I'm
linear
still
signal?
not seeing in
And
this
at
is
the same time,
the
how to
exact
prevent any
function.
unwanted electromagnetic interference. Today, we will mostly look at the first problem. And to show how this all works, we will be looking at the various signals in a circuit simulator. LT-Spice, of course. Now, changing the duty cycle can be done in
So
two
this
main
is an
ways.
amplifier
And I prepared a
simulator.
simulation to
This
show
sounds
this
like it
off.
would be a lot of
So one
fun.
method is by PVM modulation, pulse
This
width
is very
modulation.
nerdy at this point. I'm not seeing. I want to see his output here.
Ways. So with pulse frequency modulation, this upper trace, we keep the on time constant, so it's always the same on time, but the period is varied. Whereas with pulse width modulation, you keep the period constant, so the same frequency, but the on time is modified. Now, in most practical cases, PVM modulation is used since having a fixed frequency allows an easier way to filter out the signal, but both of these methods will work. And if we come back to the simulation,
No, I'm getting lost in my own explanation here. Anyhow, I think I think I need to take a break from all of that because even my own brain is like, what did I just watch? Now, what I think I've taken away from the differences in how they function is it's a lot. It's so much information. It really is. And to see that it's easier for you to just sit down and listen and then just decide on your favorite rather than looking at all the differences. But all of the differences that I was just trying to talk about and how they work and the components that are involved. And we're not even talking about the filtering on the outside and how some of the feedback is used to manage the signal. So like the output signal versus input, and if you can adjust it, like Hagel's sound engine uses some interesting feedback in order to make the signal more accurate. You've got input and output signals. If they're compared, then you can use servos. There's all kinds of stuff that's used in the signal path in order to like exact the output signal. Then you've got like noise reduction inside the chassis. You've got vibration control. You've got all kinds of other components that will either endure or last longer. The durability, the way capacitors are used in signal and their effect. It's not just a type of amp, is what I'm trying to say. A lot of people will consistently harp on like Class D being digital because it creates this sort of on-off sort of signal. Now, that's not accurate because it's still taking an analog signal. What it's doing is transforming it. It's transforming an analog input signal to pulses in order to manage the output power differently. In the Class A and AB types, the input signal in analog is being amplified through transistors in order to add current or add voltage in order to get that output. So in that sense, it's not being transformed, yes, at the cost of inefficiency. You're talking about 60% or less in a Class A amp to get input and output supposedly identical, give or take whatever else is in the amplifier. Class D is able to now into the megahertz switching and pulse, it's, if you trust a DAC to do its work, this is a very interesting point. I just kind of thought about it. If you're trusting a DAC to control any of your streaming and whatever, what's the clock rate on a DAC? DSD is operating at what's its sample rate? 512? I'm not even really sure what that relates to. That's kilohertz? Is it 512 megahertz? There are oversampling frequencies, and that's the same thing as if you take a data point along the wave and you've got as many as, possible, then it's the same thing like watching computer graphics for your eyes. Like if you can't tell the difference between the pixels and a retina screen, then your human level of perception is bypassed. If you look at a flower on the screen, it's a flower. Fuck, it's a flower. If you're listening to a power signal represented by pulses at such a high enough frequency that you cannot resolve the differences in it, and the output signal is filtered at a certain quality that it does not have that high frequency noise anymore, then that is what it is. Let me see. What's up, lads? Just walked in from the gym, ripping CDs all day. Dap. Cool. What's up? You missed a long stream here. The point is, this is what we want. This is what we want the output power to do. This is essentially everything about what the output of an amplifier is supposed to do accurately.
I'm Jake O'Neill, creator of Animographs, and this is how speakers make sound. The basic speaker design has a motor that drives the speaker back and forth, attached to a cone to translate this movement into pressure waves that travel through the air. Let's look at each part in depth. The motor. A voice coil and magnet work together to form the speaker motor.
So at this point, I'm just going to stop here and say, what the amplifier does is send current and voltage into this thing, which is essentially a resistor of a certain amount, which is usually 4 or 8 ohms, right? We know that. But it also changes based on how it's moving, because copper around a magnet creates induction, and induction can actually impede its movement. So the resistance goes up and down based on frequency, which is why you see those impedance charts where it swings up and down based on its frequency. It moves a certain way based on the mechanics of the type of magnetic force, the frequency that it is, the material that it's made out of. It creates a whole bunch of stuff. Now, what I don't know is how amplifiers respond to that impedance change, that impedance output and speaker, and you know what I mean, like damping factor, whatever they want to call it. I'm not even sure how amplifiers apply that, but their topology and how they're designed has a lot to do with how they're going to manage that. But the whole point is to make this move as accurately as possible.
Together to form the speaker motor. The voice coil has a long section of thin copper wire wound many times around a heat-resistant cylinder called the former. When electricity flows through the copper windings, it naturally generates a surrounding magnetic field.
So it creates a magnetic field of its own that interacts with the magnet.
This phenomenon is what makes an electromagnet. An electromagnet can act just like a permanent magnet. And yet, incredibly, its polarity, or positive and negative pole orientation.
It's very interesting because I know everything about a speaker and crossover and stuff, but I never looked into power ants. Thanks for this stream. I needed that. It's interesting because it's like, it's the amplifier technology from its, what you're doing is essentially like, what I find really, really fascinating is how analog works in general. Like, I'm fascinated by analog in general because it's mechanical transitions. Transistors are using one voltage level supplied through a change of a different voltage level in order to push this coil, right? They're using lower voltages and levels supplied by a power source to push higher voltage sources. And the transition between the two depends on the quality of those transistors and the management of the signal. So the feedback, the op amp, the gates on and off, like how fast they switch, how smooth they switch, how you manage those input sources, that voltage drop, overlay, their timing, all of that stuff is in the topology for how the amplifier is made before it even gets to your speakers. So yeah, amps are going to sound different because all of those different factors need to be aligned and designed correctly. I'm getting more about how they function. There's still questions that I don't quite get, and I don't need, someone who's biased on a type to speak about it, because what they do is they flower up whatever they're cherry picking. I just need an engineer to talk about how it works, what the function is, where it goes this way, that way, one way, up, way, down. If somebody else sees this on my friends list or whatever, and they want to join me next week or 2 weeks from now, whatever, please come on and help me explain this. Explain to me exactly how any of these things make a sound, or what the tolerances or the differences, or how heat changes something. Like if people say that amps and speakers have to be burnt in, what is the burning in doing? I want answers for this stuff instead of just talking points. I am so tired of people just talking shit and talking for the sake of talking without being able to explain exactly where it comes from. What's the basis to all of these changes? It's a big reason why I'm asking questions. I'm not saying I know how this stuff works, but I'm saying that I want to know more about it. I want to explain, and I did title this as a learning curve. Raj, welcome home. All right, let's get on with more explanation of speakers. And this will be the end of the video.
And magnetic intensity can be changed by altering the supplied electric current.
Right, so there we go. As the supplied electrical current pushes or pulls this back and forth, and we can see the translation between what the amplifier is doing, because the amplifier is connected to the other end of this, pushing or pulling this back and forth at any rate of speed.
It can
and that's what creates the sound wave. The sound wave needs to be smooth and fluent and coherent, with no stop gaps, no delays, no sort of what they call distortions of the input signal. Now you get a percentage of that harmonic distortion. How accurate it is to the wave, like I mean, I don't know. The harmonic distortion tells you how far off it is from the input signal. Is that true? Or is that just a number that says what it sounds like? I haven't even asked what THD actually represents.
Instantly be made stronger or weaker, reversed, or turned off completely. A large permanent magnet or natural magnet surrounds the voice coil. This magnet has a top plate and a backing plate with a pull piece through the center to focus the magnet's field through the gap.
So this is what you call the magnetic gap here, and this is measured in BL. I don't know what BL stands for, but the strength of the BL indicates how it will interact with the coil. I don't know what those numbers are. It's in the TS parameters somewhere, but that's another thing that I know about the speaker design.
An intricate electrical signal flows through the voice coil windings, causing it to move back and forth as its magnetic field pushes and pulls against that of the permanent magnet. This electrical current is a precise replica of the audio that was originally recorded.
See, that's bullshit. we know that that's bullshit. It's not a precise representation. BL stands for force factor, which is measured through the speaker's motor strength. Yes, force factor. I was like, well, BL, I mean, I've heard BL, but what is BL? Does it actually have like another name? I know it's the force in the gap. And it's changed. I mean, like a lot of the times you'll use like copper rings or silver rings, or use different materials so the inductance across the gap isn't actually pushed into or resistance against the the amplifier. So that's another thing that a lot of higher end speakers are using.
In fact, the entire sound is contained in this impossibly detailed signal.
Yeah, the more sensitive or the more accurate a speaker driver can be, the more reactive it's going to be to the voltage inputs at lower volumes, higher volumes, whatever that case may be. But this is the whole thing. The whole reason why you have an amplifier is in order to make that sound. And you're not going to be, it doesn't really explain. Yeah, so this is a part that I
known
want
as an instrument's timbre.
So it's got
or
two
unique
different sounds.
It's making a G note,
one
yes,
wave.
but it still definitely sounds like a guitar and not a piano. With a little effort, our ears can still pick out these individual instruments from the mix.
So this is an interesting
The
part
human ear
about
can discern sound vibrations between about 20 hertz and 20,000 hertz. That's a lot of available frequency to work with.
So that wave has to be...
High frequencies ride on the back of rumbling bass waves to reproduce an entire orchestra.
So they're layered. Obviously, higher frequencies vibrate faster and bass waves slower. So this coil's moving back and forth for high frequencies all the way across the lower frequencies, coupled into the same thing. So like when we have a full range speaker, the full range speaker is basically doing all frequencies from one point, which makes it very coherent. Let me see. L's length of voice coil, where L is length. So BL, what? If BL stands for force factor, how do you get L for length of voice coil wire within the field? B? That's like overhung or underhung. Oh, so... Okay, so the windings, how many windings are in that gap equals the force. It's very technical, but yeah. Yeah, exactly. So this is the big part of it. You nailed what's important about this thing is it's how each individual human body, ear and mind, our mind and brain and neurology, how individual people hear. And no one hears the same way. We can have a consensus. Yes, this is the word. We can have a consensus based on this, but no one hears the same way. I mean, the same way with color. We can have an agreement on color, and you ask colorblind people what it's like growing up being colorblind, or when they realized they were colorblind. Like, it's a sensory perception thing. What I want to understand in an argument sense is, aside from our subjectivity, really understand how and what amplifiers are doing, and then apply our psychoacoustics to its output. Because you could measure it the same, but like Paul said in his video, they don't sound the same, and there's got to be a reason why. If you can't measure it, why do they sound different? Magnetic flux density or strength of the magnetic field and the magnetic gap. So yeah, so like then the amount of coil in the gap is going to give you the force, a combined force. Anyways, I'm glad that you guys know
in
a lot
one
about this
impossibly complex,
I mean, like, this is what it's all
waveform.
about, right? This is what we want. Anyways, I'm gonna remove that, get myself all situated here. Thank you guys for paying attention to this video for so long. I really do appreciate it. I want to give you one more treat. I've got this other camera set up here. This has been my setup today. I've got the monitor audio still in here. I've got the KEF R11 metas in the background, and this is my desktop situation for the day. Something different here at the tail end of the stream, just to showcase kind of like what's going on. I do want to thank everybody. Everybody sees my I guess you can't really see it with this angle, but my Buckeye audio amps are stuffed underneath here. So I've got I only need like 1.5 feet of cable, but I've got RI cables there underneath the desk. So it was hard for my attention span, but very interesting. Thank you for the interesting topic. I mean, I needed it as much as you guys did, honestly, because calf metas are hot. Look at this. I mean, look at those things, man. Like they're really, really sexy. But I mean, imagine this was white. Like if these were just white aluminum drivers, how sexy would that be? And they're really good. These Monitor Studio 89s are really good. I really appreciate them. I have a feeling they won't be around for very much longer, but I still really appreciate them, much as I appreciate you guys for watching today. Now, I didn't get to absolutely everything and answer my questions today based on, what I wanted to handle, what I wanted to understand. But this whole series for amplifiers is basically titled Learning Curve because I want to eventually understand how each of the components, their configuration, other things that go into the amplifier types affect that sound. Now, we heard from a few people talking about their function is essentially similar. The Class D function still uses transistors, but it's using it in a different area of control. Now, the transistors, MOSFET, GaN-FET, and interesting even in GaN-FET Class Ds, the GaN-FET transistors are being used also in another way to control power signal instead of See, this is where I still get confused. Each of them are using transistors. Now, if GaN-FETs, now there's obviously transistors in a Class D design, but they're configured different. They're using it in a different way. The input signal in a Class D is being converted into pulses, where in analog it's just being amplified through transistors. So the power flows through the transistors. And in order to function right, they're being turned on, which is wasted power. In Class D, they're not being turned on as much. They're being turned on and off in pulses at certain power rates in order to reform the wave. It's very fascinating stuff. And it has a particular output sound, Some people are sensitive to it. I had tubes in here recently, and the Whammerdyne Heavy Systems has a tube input stage with Class AB output. So it's using an input the same way that the PS Audio is using. Input stage tubes are doing something. And I think that the reason why is they're at lower voltages, they're using tubes at the input stage because their linearity in that range, they're more linear in a bigger range than solid state is, apparently. But I think solid state is more durable, can handle more power, so your output is actually controlled. So if you're using tubes on the input stage or maybe even in the preamp, and then you're able to use very high quality, accurate, distortion-free solid state on the output, and you control that the right way, that's like the blend of the right blend of two worlds. But I feel like in my experiences, tubes were doing something with the space. They were either maintaining the space or they were adding space. Like, I don't know if there's a coloration there or if like the recordings have that kind of feel and I'm just realizing it. I need more about this. So like I said, if any of my friends, engineers, designers, whatever, want to talk about something in the comments, assuming this video doesn't get copyright struck because of all the different clips I use, if anybody wants to talk about anything in the comments, let me know. If you want to join me and talk about how the design implementation components and class types generate a sound difference, like how they're equatable, I would love to hear from people. I'd love to hear really good examples or analogies or metaphor, whatever you got that explains it better and better and better. I'd love to have people on to explain exactly how it works. So thank you everybody for joining today. This has been a long one, an hour and a half I'm seeing. I appreciate you. Thank you very much for the support and joining and being here on the channel, for watching, for sharing, for adding your inputs, your reflections, all of that stuff. I'm going to get out of here, get myself rested. It's a very cold night tonight. It's like going down to minus 14 Celsius here, which is ridiculous. So I need to make sure that everything is set up for that. I will be back again throughout the weekend. I've got an event on Saturday at a store, so I'm going to see if I can do anything live from the store. On Sunday, the Mako Macarias will be leaving the house. Then I need to put the KEF R11 metas in the room, start that whole process. And between there, intermittently, if you watch my Instagram and Facebook, also my YouTube shorts and channel stuff, I will be doing a little bit more with the monitor audios. The Studio 89s will be here at the desk for a little while, and they sound really amazing. There's a couple clips already out there on Instagram. They sound great. Thank you so much for being here. I do appreciate it. I need coffee. Yeah, maybe not coffee. 23 Celsius? Damn, that's actually pretty good. All right. I'll see everybody in the next video. Thanks very much for being here. Like I said, if anybody's got like designing, amplifier designing skills or anything like that, there's a bunch of designers that I know. I'm wondering if any of them would join me for 10 or 20 minutes or whatnot. I'll have to ask them, send some emails out. I imagine some of them would be interested in doing a talk, just so I can kind of understand like what's going on, the use of different things, and without giving away their secrets. All right, everybody. I'll see you in the next one. Thank you very much for being here. I'll catch you on the flip sides.